In this quiz, we're looking at another electrochemical cell, starting with this shorthand. And note that for this week, what's been covered is non-standard electrochemical cells, and that may be relevant for further questions. But to begin with, all we're looking for is the oxidation and reduction half reactions that occur, and we want to label which is at the anode and which is at the cathode. And so breaking into half reactions is where this notation is really helpful, because on one side of the double line, we have the oxidation, and on the other side we have the reduction. And so that's exactly what we have here. Barium to barium-2, this is on the left side of the double line. That is our oxidation. Barium is losing 2 electrons, and this is the anode. On the other side, we have copper-2 gaining 2 electrons to become solid copper, and therefore being reduced. This is the reduction, and it's at the cathode. That's all we need for the first part. The next part, we want to determine the number of electrons that are transferred in the balanced redox reaction. And I think the best way to do this is first to state the balanced redox reaction, which begins by combining these half reactions. There's 2 electrons in the product and the reactant, so we don't need to modify anything like that. Remember that when we combine half reactions, what we need to cancel out is the number of electrons in the oxidation and the number of electrons in the reduction. Therefore, no electrons will appear in the balanced chemical reaction. But it's 2 on both sides, so here is our balanced chemical reaction. And sure enough, what this shows is that 2 electrons are moving from barium to copper, and we can determine that N equals 2 in this case. As we write this chemical reaction, what it's associated with is the transfer of 2 electrons, and we can see this from the balanced chemical reaction itself, as barium goes from having 0 extra electrons to 2 fewer, copper goes from having 2 fewer to having the same number as protons. So it is implied within the balanced chemical reaction alone, but it can be really useful to see that number explicitly in the half reaction combination. Okay, so now we want to calculate the standard cell potential and indicate whether it's spontaneous or non-spontaneous. We have our barium reaction right from this shorthand. Barium goes to barium-2 plus 2 electrons. And note that this is an oxidation, so the value we take for the corresponding reduction off of Appendix L, we're going to flip the sign of that because this is actually the reverse of that reduction reaction that appears on the table. The copper reduction is exactly as it appears on the table, and so we just take that half reaction and half cell potential directly from Appendix L. Now when we combine, we added the 2 half reactions before to get the balanced chemical reaction, and the same thing can be done with these cell potentials. We've already reversed the sign of the oxidation, and therefore we've already done one negative of that value. And so when we add the oxidation to the reduction in a way that cancels the electrons, we simply need to add their corresponding half cell potentials. So 3.24 volts. Now we want to think about non-standard conditions. And so for part D, what we're saying is that we start with a standard cell, and note that reactant will be consumed and product will be formed, just like every other chemical reaction. And so as this runs, the copper concentration and the barium solid will be depleted, while the barium-2, the barium solution, and the copper solid will be created. So still reactants becoming products is part of this, and it'll happen slowly over time. And after a while, the copper concentration has continued to drop and the barium concentration has continued to rise to the point where the barium is now 1.75 molar and the copper is now 0.25 molar. And so after it's run for this time, we want to calculate the new cell potential. And here's where we want to use the Nernst equation. It's non-standard conditions, and what this says is that the standard cell potential, E naught cell, minus this term, which contains Q, will combine to be equal to the cell potential that we're looking for, right? So basically the composition matters. That's what this is saying. And by using the standard cell potential and our composition, we'll determine the new cell potential. So let's break down the different parts of this equation. N is equal to 2 moles of electrons. We've determined this in part B. The cell potential is positive 3.24 volts. This is from part C. And again, we've done these parts already, but if you're doing a non-standard cell from the very beginning, all these previous parts are things that you need to do. Q here is the barium concentration over the copper concentration. This is where it's a little deceptive to look at the shorthand notation because it may look that barium is a reactant and copper is a product, but actually copper-2 is a reactant and barium is a product, so these come from the balanced chemical reaction, and breaking the shorthand into that balanced chemical reaction is really important. We determine that Q is equal to 7 in this case from that ratio. And from there, we simply use Nernst, calculate the non-standard potential. It's based on that standard potential of 3.24 volts minus the constant over n equals 2, log of 7. That describes the composition that we're looking at, right? How it shifted from products to reactants based on how it changes from standard conditions. And when we evaluate that, we get our non-standard potential is slightly lower, slightly more products than reactants. So it will be slightly less forward pushing compared to before, slightly less spontaneous, and we see that in the cell potential as well. The value is still positive, but a little bit smaller than what we calculated when everything was 1 molar.